In the second part of our section 6.8 video, we're going to focus on exponential functions. Our first part was all about logarithmic functions, and we will talk about derivatives and antiderivatives for exponentials, as well as what to do if it's an exponential that does not have base e, which is usually the easiest one to calculate. So we'll start with derivative. The most basic derivative is the derivative for e to the x, which is e to the x. So nice and simple. But don't forget all of your Calculus 1 special derivative rules. We could potentially have products or quotients or composites there that we have to deal with, but the trick to remember is anytime you take the derivative and the outside part of the function is e to a power, the derivative is always going to contain e to that same power. Now, if we want to do this with a different base, say 3 to the x, it's still considered an exponential function, and the derivative for an exponential function always contains itself. And the difference here is that we are going to also multiply by natural log of that base. One thing hopefully that you got out of algebra is that exponentials and logarithms are opposite or inverse functions, inverse operations. So hopefully it makes sense here that when we did derivative for logs of another base, we divided by natural log of the base. When we do derivatives for exponentials of a base, we're multiplying by the other base. So since it's the opposite type of function, but still related, we still work with the same bones, so to say, but we do the opposite operation. So with logarithms, it's division. With exponentials, it's multiplication. You may have also seen this formula at one time or another, and this is really just an explanation of how to do chain rule. If we don't have just x in our exponent but some function of x, we're still being asked to do the derivative of an exponential function, which always is itself. But then we also have to multiply by the derivative of the inside function. And with exponentials, the inside function is the exponent. So anytime you do chain rule with exponentials, the inside function should be your exponent. So look at a couple quick examples and then we'll go on to antiderivatives. So the first one we're going to try is to find the derivative for e to the negative x squared plus 4. So you should recognize this as an inside function and an outside function. We're going to use chain rule. The outside function is the exponential, and the derivative for an exponential function is always itself. Completely unchanged, exactly the same function that we started with. But because there's an inside function, this is considered a chain rule, and we also have to multiply by the derivative of our inside function, which is our exponent. And the derivative of negative x squared plus 4 is negative 2x, and that's multiplication. You would typically see this with the negative 2x moved to the front. That way we wouldn't accidentally confuse it with subtraction. quick example with quotient rule. If we want the derivative for 5x squared divided by e to the x, since the function we want the derivative for has x's in two different locations, we need to figure out how those functions are being combined, and this is division. That means we use quotient rule. Quotient rule says you start with the derivative of your numerator, which is 10x, and multiply it by the original denominator, and then subtract original numerator, derivative of the denominator, and the derivative for e to the x is e to the x, all divided by original denominator squared. So we can clean this up a little bit, and there's some algebra simplification we could do as well. What we have here is 10x e to the x minus 5x squared e to the x all over e. Now, one power raised to another power, they get multiplied, so that's e to the 2x. Now, every single term in this expression has an e to the x, so we can factor the e to the x out of the numerator and cancel it with one of the e to the x's in the denominator. So I'm going to take one away here. If I take one away here, there's technically 2, and that will leave me with just 1. So for our final, most simplified answer, we get 10x minus 5x squared all over e to the x. And one more real quick with a different base besides e. If we want the derivative of x cubed times 4 to the x power. Again, I see x in two different places, and the functions containing those x's are being multiplied. That tells me I need to use the product rule. So product rule says take the derivative of our first function, which is just power rule, 3x squared, multiply it by the original of the second function, plus original of first function, and then derivative of the second function. So our second function is an exponential, which means its derivative is always itself. Because it's base 4, we also multiply by the natural log of the base, so natural log of 4. There isn't really much we can do to clean this up unless you wanted to do some factoring, which you don't need to do because it's not going to help us with any canceling or simplifying. So really this is just 3x squared times 4 to the x plus x cubed times 4 to the x natural log of 4. Now there are several like terms or like factors within those two terms that we could factor out. We really aren't going to factor though unless maybe there's a denominator we could cancel with, but just so you could see how that would work, both of these terms have at least an x squared in them, and they both have a 4 to the x in them. So we could factor out x squared 4 to the x. If we did that, all we'd have left is 3 plus x natural log of 4. It's the same exact thing, it's just factored, and it's really not necessary, but it's possible. So finally, let's talk about antiderivatives with exponentials. We know that the derivative of e to the x is e to the x, and antiderivatives just perform that operation backwards. So the antiderivative of e to the x is e to the x. It is going to be very common for us to see something else in that exponent, so we may have to do u substitution for the exponent. The exponent is considered your inside function. If we're not working with base e, so just a general formula for antiderivative of an exponential with any base, well, we know it's always, the antiderivative will always contain itself because we said the derivative always contains itself. With derivatives, remember, we multiplied by natural log of the base. And antiderivatives are inverse of our exponentials. They're inverse of our derivatives, excuse me. So for derivatives, we multiply by natural log of the base. That means with antiderivatives, we're going to divide by natural log of the base. So I'm going to say times 1 over natural log of a plus c. If you want, you could just combine them into a single fraction. A to the x all over natural log of a plus c. And it is common for us to have to do u substitution here, and keep in mind that almost always our exponent is what we're going to be substituting for. So we'll look at a couple of quick examples. Let's find the antiderivative for 3 to the 2x plus 5. Because we don't have just a single linear x in our exponent, we're going to want to do a u substitution for the exponent. So we're going to let u equal 2x plus 5. That means that du is going to equal 2 dx. And besides that 2 coefficient in our exponent, there's no other 2's in this problem to get rid of. So I'll divide that over and keep it in the problem with my du. So now I have a substitution for my dx. dx is going to get replaced with a half du. So now we've got the integral of 3 to the u times 1/2 du. And that 1/2 is just a coefficient. You really could pull it out front and ignore it until the end if you wanted to. Well, the antiderivative for 3 to the u, antiderivative for any exponential, is always itself. And because it's not base e, we also have to divide by natural log of that base. So we'll get this back in terms of x and write it as simple as possible. This is technically 3 to the 2x plus 5. That's my 3 to the u, all over 2 natural log of 3. So the 2 came from our 1/2, and then we have natural log of 3 from our antiderivative. This one can be kind of tricky, but if you keep in mind the pattern that we've already seen, if we're doing the antiderivative for exponential, if our exponent is not just a single linear x, we are almost always going to have to do a u substitution for the exponent. So don't worry about that square root x in the bottom right now. Hopefully that will work itself out with our u substitution, but we are going to replace the one in the exponent with u. So to take the derivative here, we're going to have to think of that square root x as x to the 1/2 power. And we get du equals 1/2 x to the negative 1/2 dx. And if we rewrite that a little bit, it might be more clear exactly what this means. X to the negative 1/2, well, negative means it wants to go in the denominator, and 1/2 means it's still a square root. So the only difference now is we've got square root in the denominator. And look right here, we do have root x in the denominator, dx to get rid of. So that root x in the denominator dx, we can substitute them just as a chunk. We don't need the 2 though, so I'm going to multiply that 2 over since it's in the denominator right now. So 2 du can replace that 1 over root x dx we have there. When we do that, this integral becomes e to the u. The root x dx is going to get replaced with 2 du. And we have no fraction anymore because we got rid of the denominator. The 2 is just a coefficient. If you want, you can move it out front and just worry about it at the end. The antiderivative for e to the u is e to the u. And the last thing we need to do is just rewrite this in terms of x. U was square root x.